created by MindSticks Foundation Trust.
Hello, students, and welcome to today's Explainer. We've got a fantastic lesson ahead. Today, our agenda covers 1. The general area ratio, 2. Triangles with equal heights, 3. Triangles with equal bases, and finally, 4. Solving textbook examples together.
Let's jump right in. Section 1, the general area ratio.
Now, recall this standard formula we all know so well. The area of a triangle is equal to half multiplied by the base multiplied by the height. Keep this firmly in your mind, students, because this simple, elegant equation is the absolute foundation for everything we are going to deduce today.
Now, observe the two distinct triangles we have right here. One triangle has its own specific base and height, and the second triangle has a completely different base and height. What happens if we want to find the ratio of their areas? Well, we simply divide them. When we put the formula for the first over the formula for the second, something wonderful happens. That half in the numerator and the half in the denominator, they cancel each other out completely. So the crucial takeaway is this general rule. The ratio of the areas of any two triangles is simply equal to the ratio of the products of their bases and their corresponding heights. It's literally just base 1 times height 1 divided by base 2 times height 2. Very simple, isn't it?
Let's move on to Section 2, triangles with equal heights.
Direct your attention to the triangles shown here. Notice carefully that both of these triangles share the exact same height, which we've marked as h. Think about our general ratio formula for a second. If h is perfectly identical in both the numerator and the denominator, well, you guessed it, we can cancel it right out, just like we canceled out the half earlier.
And this brilliantly illustrates our first special property. Because those heights cancel out, we are left with a very clean, very elegant rule. The ratio of the areas of two triangles with equal heights is simply equal to the ratio of their corresponding bases, or, mathematically speaking, b1 divided by b2. You don't even need to worry about the heights anymore. The bases tell you everything you need to know about their area ratio.
All right, Section 3, triangles with equal bases.
Now, what is really interesting here is how these two triangles are positioned. Look closely. They are both sitting directly on the exact same base, that shared horizontal line segment at the bottom. The first triangle has a height of h1, and the second has a height of h2. If we write out our ratio equation, that common base is sitting in both the top and the bottom. So, following our same exact logic, that shared base value cancels right out of the equation.
We can now safely conclude our second property. Under this specific condition, where the bases are equal, the ratio of the areas is just equal to the ratio of their corresponding heights. It simply becomes h1 divided by h2.
Let's pause for a moment and contrast these two conditions so you can memorize them easily. It's a beautiful, inverse-like relationship. If the heights are equal, you look at the proportional bases. If the bases are equal, you look at the proportional heights. The constant term simply disappears, and the varying term dictates your ratio. Make sure you fully grasp the symmetry before we move forward.
Excellent. Now it's time to apply this logic. Section 4, solving textbook examples.
Focus your attention on this shape right here. This is a solved example from your textbook featuring a parallelogram. Now, geometry problems absolutely love to play hide and seek with us. They often hide our special conditions inside other geometric shapes, just like this parallelogram. So let's uncover those hidden triangles together.
Let's patiently walk through the logical steps. First, because this is a parallelogram, we know the top and bottom line segments are perfectly parallel. Second, we have to remember a crucial fact. The perpendicular distance between parallel lines never, ever changes. Therefore, any triangles drawn between these two parallel lines will have the exact same height. The height is firmly locked. Third, look at the two distinct triangles resting on that shared bottom base. What do we have? They have equal heights because of the parallel lines, and they share an equal base. Both of our conditions are met. Therefore, step 4, their areas are perfectly equal. The ratio is exactly 1 to 1.
Before we wrap up, I want to reiterate this. Remember this mental cheat sheet. These are the 3 golden rules you absolutely must anchor in your minds. First, the general ratio equals the ratio of the products of their bases and corresponding heights. Second, for triangles with equal heights, the areas are proportional to their bases. And third, for triangles with equal bases, the areas are proportional to their corresponding heights.
To close out our explainer today, I am presenting you with this unsolved figure from your upcoming practice set. Look closely at these two triangles. I really want you to observe that shared central line segment and notice exactly where those right-angle perpendiculars are located.
Here is my challenge to you before you start your homework. Which of our golden conditions applies to this figure? Is this a case of equal bases, or is it a case of equal heights? And how are you going to use that knowledge to solve for the area ratio? I will leave you with that puzzle to ponder. You now have the exact tools you need to unlock the answer yourself. Thank you for joining me, students. Keep practicing, and I will see you in our next explainer.